Hello and welcome to CIC Start Online webinar here at Glasgow Caledonian University. My name is Branka Dimitrijevic and I will moderate today's event. As always at the start of our webinars, I have to say that our webinars disseminate the outcomes of feasibility studies and academic consultancies undertaken through our project. The project supports collaboration between 7 Scottish universities and small to medium-sized enterprises to develop and test innovations for sustainable building design and refurbishment. The project is funded by ERDF, European Regional Development Fund, and Scottish Government. This is a live event, so in the case we hear alarm, we will have fire alarm, we will have to stop, but we will continue later. If you can join us, that will be fine, but if you cannot, the video recording of this webinar will be available on our website in due course. We plan to finish around the presentations around 1:30, and then questions will be answered by our speakers. You can start using chat facility immediately to ask any questions, but they will be answered after 1:30 o'clock. And we plan to close around 2 o'clock. If some questions could not be answered during the webinar, the speakers will reply to them by email. So the title of today's webinar is Life Cycle Carbon Analysis of Novel Board Material. And this was a study undertaken by Glasgow Caledonian University in collaboration with Duncryne Ltd. And the speakers are Dr. Charles Russell of Glasgow Caledonian University and David McBeth of Duncryne Ltd. The presentation will start with David McBeth. So David, please start with your presentation.
Thank you, Branka. My name is David McBeth. I'm a director of Duncryne Limited, which is a Glasgow-based company set up in April 2011 to source sustainable building materials from the Far East to the UK, Europe, Middle East and Australia. The principals of Duncryne are myself, Keith McNair and Craig McKenzie. Keith and myself have 20 years experience in property investment, development and contract procurement, working for companies and property funds like Prudential, Aberdeen Asset Managers, Bovis Construction, Miller Developments, etc. Craig actually lives in Shanghai, where he's been based for a number of years, and he has 20 years experience in product sourcing for clients in the UK and Europe. There's also an office established in Shanghai with professionally qualified bilingual Chinese staff, and we found that this sets us apart from most other suppliers of magnesium oxide materials, which is the Econic board, because they have an understanding of the manufacturers, the cultural differences, just the way of doing business in China. Duncryne are the sole suppliers of Econic performance systems worldwide. These systems provide a range of construction and engineering related applications and solutions. We are seeking to work in partnership really with like-minded companies who have materials, systems or ideas which can be combined with our products to create new systems and new applications for both construction and specialist engineering applications. Next slide. Okay. Just a brief background or history to magnesium oxide, or MgO. Blends of magnesium compounds have been used for centuries, millennia throughout the world. In fact, the Great Wall of China and the stupas in India used magnesium-based compounds in their cement mortars. Given the magnesia's characteristics of high fire resistance. It's used extensively as a furnace lining for steel furnaces, kilns and reactors, and most modern application is actually used in the nose cone for the space shuttle. In Western construction, the Portland cement has basically predominated throughout the 19th and 20th centuries. It creates a lot more energy to create Portland cement. It's not as environmentally friendly, but it is cheaper. However, in China and the Far East, where most of the magnesium ore is located, they've continued to use magnesium-based products for the construction industry. Some high-profile examples are the Beijing Olympics in 2008, where the athletes' village was predominantly made from magnesium oxide. It was also used as an internal and sheathing board in the Taipei 101 Tower in Taiwan. And there are some, I don't know if you can see, there are some samples of our product. It comes in a range of thicknesses, from 3mm up to 50mm. It can be routered, it can be nailed, stapled, screwed, just like timber. It can be worked with the same tools as timber. It can also be used to form SIP panels, the example of which is here. So it's got a lot of applications. There are many manufacturers of basic MGO products in China, supplying boards primarily for their local market. There are only a handful, however, who we believe can supply to Western construction standards. We've deliberately chosen to go to one of the better manufacturers and to source a quality product. Because we've developed this product with the manufacturer, we've had to carry out a full range of testing in the UK to make sure it's fit for purpose. And through our Shanghai office, we've analysed a number of manufacturers. We've got our chosen one, and we have an exclusivity with that factory for this product. The key to our performance criteria is ensuring that we only use the highest quality raw materials and that there's rigid controls of the manufacturing process, which Charles will expand on later on. And the next one. Next slide. Just as an example, because we've developed a range of specifications, we've had to carry out our own extensive range of tests. This is a list of the tests to BS and EN standards, which we've had carried out by CIRAM, principally by CIRAM, based in Stoke, a UCAS accredited testing authority. This list will keep growing because it's a main function of our business that we think our testing has to continue to evolve as applications and systems are developed, new uses are found. We need to keep our testing up to date. We believe that Econic boards are the most extensively tested MGO-based product in the UK at the moment. Copies of test results summaries are available to download at our website, www.econicboard.com, and copies of the actual test data will be made available for those who are interested. Next one. Following the tests that we've carried out, there's a few examples here of the benefits of Econic products. First of all, it is Euroclass A1 non-combustible. It's been tested by the UK Timber Frame Association in their most recent round of fire tests, and it has been confirmed as compliant with Category C rating in their UK TFA fire design guidance to separating distances. This guidance has been approved by the Health and Safety Executive, the Association of British Insurers, the Fire Protection Association, Chief Fire Officers Association, Fire Brigade Union, etc. So it's fully compliant and good for timber frame manufacturers to use in lieu of USB. It's also a Category 1 racking board, and we've tested it on both timber and metal frames. We can use it therefore as a sheathing board in lieu of OSB instead of plywood or chipboard. Econic board's got an exceptional bonding surface, and it makes it ideal for adhering different substrates, laminates, insulation, like our SIP panel. fixing wall ties, external cladding panels, etc. We've also had it tested to MOTE 22 and ETAG 24 for render carrier board, and it's passed for both painted and render finishes. We also think it's good as an off-site board. We see it as an ideal replacement for the timber, as we said, and for use in off-site and volumetric construction. Econic board has got a very good vapour permeability, which makes it ideal as a board for use in a breathing wall construction. Econic boards are inert, non-toxic, free from formaldehyde, benzene, solvents. It's got no oil-based chemicals, therefore contributing, we believe, positively to a healthy indoor environment. It's also got a severe duty rating for impact, which we think makes it ideal for high traffic areas like schools, hospitals, institutions, student accommodation, etc. Because Econic board is unaffected structurally when it's in contact with moisture, and because of its good adherence properties, it makes it an ideal tile backer board for both domestic and commercial applications. And finally, on its own, it makes a good decorative finish panel. It can easily be taped and filled and simply painted as a finished product. Next one. This slide here demonstrates how versatile Econic board is. It's an all-round solution for many construction applications, and it compares favourably to competing materials in quite a few aspects. Given all these uses and potential uses, we have a number of applications and sectors where we think Econic board, where it is being used and where we would like it to be developed to be used as a shearing board, the most simple application, a passive fire applications for cladding of structural steelwork, etc. SIP panels, it has been tested and is being used by a couple of SIP panel manufacturers at the moment. Modular construction, non-combustible thermal and acoustic upgrading systems. Here we are in discussions with a number of manufacturers to create new products to attach their insulation systems, whether it be for thermal or acoustic applications, to create a non-combustible solution. Finally, the biomass and agricultural uses are something that we would like to expand into, but also any ideas from any of the participants today, we'd be delighted to hear what they may be. And finally, I'd like to, because we know that the board, what it can do and its performance criteria, we were also very keen to know about its sustainability aspects. We know the process is to manufacture the board. We believed it to be low carbon, low energy use, but we wanted this verified. So through a Kickstart programme, we were very pleased that Charles came on board to carry out a full life cycle analysis. I'll just hand over to Charles now to talk you through his studies.
Thanks, David. Let me just push on to this. Yeah, we were delighted when David approached us to really undertake a life cycle carbon assessment of the Econic board. And I'm just going to go through that. So it's a life cycle analysis, but we focused on the carbon. There are many, many different elements in most life cycle analysis, but we're really just dealing with the carbon element. So why life cycle analysis? Why look at that? Why is that important? And why seek advice on that? Well, the first thing is it's a comprehensive analysis of the greenhouse gases associated with the production and whole life use of the product. And it's an approach that's been highly favoured by the construction sector. More and more pressure is on the construction sector because of its high association with greenhouse gas emissions in UK inventory, but more broadly too. And it's understood that a lot of materials have emissions associated with what's called the embodied energy, but also end-of-life processes that are maybe not captured in traditional inventory approaches. So the application of undertaking a life cycle analysis really allows all the elements of the product's life to be captured, and also allows for us to look and see, well, what else could be done to improve the product. For life cycle analysis, there are ISO standards available, which is also of interest to the team at Duncryne, and we wanted to set it up so that it would be ready for undertaking that kind of assessment. There's a high degree of transparency required, which in of itself is a challenge, because we were doing all the work from here in Scotland and relying on obtaining information from colleagues in China, but we did manage to obtain most of it. And finally, the robustness of the process does allow us to look and see what can be done to improve it in terms of carbon reduction solutions. And that should really be part of any of these processes, is to look and see how do we further improve, not just to accept that that's it and there's nothing else we can do, but actually to further tweak the process. Let's have a look and see what's included in this life cycle analysis. First of all, and it's very important, we looked at the embodied energy where we could of the primary ingredients. I'll come to the primary ingredients shortly. Secondly, we looked at the product manufacturing process, where the product is manufactured in southern China, and we've taken as much detail as we can to work that out and present that here. There is some limitation on what we can and cannot present for confidentiality reasons, but I think what we'll show here today will give you a good sense of what the life cycle analysis comes out at. Transport to China, from China to the UK, there's obviously transport of the raw materials within China, and we've included that, but also one of the criticisms that's often leveled at companies importing products is that there's such a high amount of emissions associated with the transportation of the product to the UK. So we've looked at that, of course, that's included in our life cycle. We've looked at the waste management element, and we've also looked at carbon dioxide absorption. It's a very important feature of this product. I'm going to go into a little bit more detail about that, because it affects the whole life cycle element. And we've assumed that 95% of the emissions that are associated with the manufacture of the product and life cycle of the product are captured by this analysis. These are the Econic board ingredients, and I'm not going to give you the proportions that are in the board, that's confidential, but it is a magnesium oxychloride board. It's a type of cement that's produced. So the main ingredients are magnesium oxide and magnesium chloride. There's also sawdust, which is used as a filler, and perlite, which is also used as a binding agent. And the product also has a fiberglass mesh through it, which provides a structural support for the product. Finally, there's water in the product, certainly in the manufacture of the board. The actual final moisture content of the board is very low. China's a big country. We did our best from the office here in Glasgow to understand what from David and his colleagues what was happening in terms of the different components. They're simple components. A magnesium oxide is produced in a powder form, and it's manufactured from calcining. That's using heat of a naturally occurring compound called magnesite, which is calcium carbonate, magnesium carbonate, with some calcium carbonate, but very low levels of that. It's found they have large reserves of this. I think that China has the largest reserves of magnesite in the world. And there are very large reserves of this in northern China. Calcining is also done there. There's a good availability of local coal there too. So the heat is provided by coal-fired kilns. The other products are slightly closer, or a lot closer, to the main factory in Guizhou. Did I say that right? Guizhou, right. So the other main ingredient being magnesium chloride comes from the island of Hainan, which is just off the south part of China. It's magnesium chloride is actually a byproduct of salt manufacture. It's a low carbon process, but we'll discuss a little bit about that in a moment. The other products, the sawdust comes from 100 kilometers away, and the other two parts, perlite, is also readily available in Guangzhou, and the fiberglass is manufactured in Fujian, which is transported by ship to the factory. These give some of the details. So there's significant amount of transport associated with moving a lot of these raw materials to the main factory site in Guizhou. So that really just gives you an idea of what we look at. Now, I've used, in calculating greenhouse gas emissions, I've used, really for sake of simplicity and what's best available and what we can most likely verify, we have used the emissions factors that are produced from DEFRA and DEC. So these are updated annually and are very useful. What that document provides is publicly available is emissions factors for all kinds of different transport types. We've assumed bulk carriers for the products by ship, and we've also included the road transport, which would be articulated vehicle. And calculating that these elements, it's effectively the distance multiplied by the emissions factor, and you need the tonnage that would normally be used. So this is a sort of fairly important element of the raw material. But when we started to look a little bit further, there are obviously carbon emissions mainly associated with fossil fuel combustion. And because coal is being used and magnesium carbonate is being converted to magnesium oxide, CO2 is being produced in that reaction too. And because magnesium oxide is one of the primary ingredients, it meant that really we had to look at this in some detail. Now, I'm getting information about this quite difficult from the Chinese end, so we've had to rely on industry-sourced work that indicates what is involved in terms of carbon emissions regarding magnesite production, calcination. So the magnesium oxide is produced by calcining it in these kilns for 2 hours at 700 degrees centigrade. And as I said, they use these coal-fired kilns. There is also the mining element of the magnesite, the magnesium carbonate. We assume that that is 1 litre of diesel per tonne of the magnesite mined, if you like. That's the assumption we've taken, and that's from publicly available literature similar. You can see that as we work that out, that gives us a figure of just over, it's 0.006 kilograms CO2 per kilogram magnesium oxide. Then the magnesite calcining, just to give the comparison, is just under 1 kilogram of carbon dioxide per kilogram magnesium oxide produced. So it's a huge part of the process in terms of the carbon emissions, and that we'd expect that because effectively you're driving off an equivalent, a ton of carbon dioxide for your ton of magnesium carbonate. So that's how it works. So that gives us something to work at. Then we then looked at the magnesium chloride. What happens in the reaction? The magnesium oxide and the magnesium chloride react together, and it's a very important element of the structural structure of the iconic board is the reaction of these two compounds. But the magnesium chloride itself is really a byproduct of salt extraction. So there's really very little energy required. What happens is it's actually a low energy process called the Dow process, producing magnesium chloride production. So this is actually how it's done in Hainan. This is a very simplified processed map of what happens here. Obviously, we're not interested in producing magnesium metal or chloride. That's the electrolysis part of the Dow process, which is energy intensive, uses a high amount of electricity. But really up until that point, you really have calcined dolomite mixed with seawater, which has already been reduced in moisture content. You precipitate it out, and then through a series of stages, you produce hydrous magnesium chloride, which is then dried, and we can that's then the product that's shipped to the factory and mixed. It's important that the purity levels of the magnesium oxide and the magnesium chloride are robust. It's one of the things that our colleagues at the factory have told us, is that having impurities does impact the quality of the final product. The other parts, I'm not going to go into too much detail how we carried out the carbon assessment. Sawdust we've assumed as a waste product, so we've just taken the sawdust would either be disposed of in landfill or combusted, so we've assumed that's a waste product and there's no carbon associated with that. The perlite, we've used a standard emission factor from the University of Bath's inventory of carbon and energy, and it's pretty much a text, a reference that we've used consistently throughout this work. What actually happens when all these products get to the factory? They're stored in a way where they're kept dry. This is important. The storage conditions seem to be essential. So the compounds are mixed in the various proportions required, and it's mixed into a paste which is then poured onto a PVC molding plate. So it's a low temperature, there's no heat required to actually make the paste. But when that molding plate is there, the glass fiberglass mesh is added, is sort of placed into it, and is allowed to then dry for 48 hours at 40 degrees C. Now, I'm told, haven't been there, but I'm told it's a very warm part of the world. Now, I don't think it will be 40 degrees centigrade all the time, but it's obviously the temperatures required to actually get to 40 degrees are pretty low. So it'll be assisted heating. So we have actually looked at that. So when the product is then dried, the drying process, that is actually quite critical to what happens here. But in the electricity that's used in the factory, we've obviously got lighting and machinery for using, for example, the conveyor belts, and there's cutting and polishing machines. There's obviously going to be some heating in there. The annual energy use from the factory, from the factory in China, is 166,000 kilowatt hours. And we have the greenhouse gas emissions factor for the grid electricity in China, which is that number there, 0.7584. It's actually quite a bit higher than the grid electricity in the UK. Mainly that's because they use more coal than we do here. So that tells us what's happening in the factory. Then finally, and this is often the step that there's some concern about in terms of moving the product, but actually in terms of understanding that, it's in terms of the life cycle analysis fairly straightforward to undertake. There are three main segments to the journey. We haven't included, for example, things like elements like loading of the board by forklifts at either end. We haven't included that. We've assumed that that's going to be much smaller part of the total emissions, but except that will have an emission, but that just is, we've just included what's going to be the bulk. Factory is 30 kilometers from the port. That transportation is by road. And then we have a longer journey of 18,700 kilometers from the port to Grangemouth, and that's by bulk carrier. And again, there's a trip, a road haulage in the UK and in Scotland from Grangemouth to Inchinnan, where the company Duncryne have their storage facilities. So we need to, in terms of the usage, from that point, from the storage to wherever the product then goes, there is an element, but we don't know how far that's going to be. So we've left that part out as that's what happens when it moves to wherever it's going to be used. But as you'll see, it's such a small part that it's not really so significant. What I do want to look at finally is, not finally, but is the waste management part of the life cycle assessment. At some point, we know that these products have probably quite a long lifetime. I don't know how long that lifetime is, but they have a good length of life. And we do need to work out in this what happens at the end of its life. Now, being a construction material, it's likely that it would be recycled pretty much straight away. It could go to landfill with a very low percentage of carbon. The carbon is in the form of the sawdust. That's the only carbon that's in there, apart from the absorbed carbon dioxide. But in terms of organic carbon, which is in terms of greenhouse gases, that's what's going to be converted to methane or to carbon dioxide. It's a very, very low amount. We say that that's pretty much nominal, and it's likely that in this process, and it's probably something that we need to look into further for its uses, end of life uses, that it would be not significant at all. What is important is that when the product is broken down, there will be further carbon dioxide absorption. So I'm going to cover that in this next bit. Magnesium oxide is reactive with carbon dioxide and water in the environment. If you just take carbon dioxide and magnesium oxide, it will bind to a carbonate. Now, in this reaction, you have magnesium oxide, magnesium chloride in a mixture with water. And we know from the chemistry, which we can't really talk about in too much detail here, that a significant amount of weight is added to the final product. And this can only be from the atmosphere. There's nothing else being added in the system. So it has to be carbon dioxide. There's been other work on magnesium oxide boards that's been published. And so we know that this is what happens. The actual structural chemistry of this, physical chemistry of this is actually more complicated than it just becoming a carbonate, magnesium carbonate. And if you want more information about that, please email me. It's probably too much to talk about straight away in this particular presentation. During the manufacture of the board, 20% of the final weight of the board is actually carbon dioxide. This is very significant. So it's actually reabsorbing CO2. And when that's actually converted back into magnesium carbonate, or at least into carbonates, and held in the structure of the composite material. So it's also assumed, we're also making an assumption that at the end of life, what will eventually happen, the remaining magnesium oxide will be converted back to magnesium carbonate at the end of life process, at the end, in terms of its environmental fate. So we've made that assumption. And so let's look at some of the numbers. We're kind of getting into the final stretch, if you like, of the presentation. But what we were interested in looking at was really, well, what are the main elements in the whole process? And we can see that if you look at it, obviously the main element is the calcining, the conversion of magnesium carbonate, magnesite, to magnesium oxide. Now, if gas was to be used instead of coal, which is the case in other parts of the world, they do this in Australia where they calcine using gas instead of coal. They have policy instruments in Australia that really has forced them to shift from coal to gas, because otherwise it's just so costly on the final product. They don't have that issue so much in China, so this is more of a how do we make the product even better. As you can see, it is a low carbon product. We've assumed that there's negligible emissions from the magnesium fluoride, but there is obviously the transportation element from magnesium fluoride and from the sawdust. The fiberglass we've taken, it comes from the life cycle analysis work that's been done by the University of Bath, the IC, the Inventory of Carbon and Energy. And perlite, it's naturally occurring perlite. There is some energy associated with grinding the product up and getting it to a point that it can be used. And water is just assumed pumped water, which it is pumped water that the factory uses, and there's very little waste water produced in this process. So in terms of water treatment, that's an insignificant element. Product manufacture, we've got the, sorry, skipped over the CO2 absorption. That is effectively 0.2 of a kilogram per kilogram of the product. And then you've got the rest of the emissions associated with the factory. So if you actually compare product manufacture in the factory compared with the actual carbon dioxide produced by calcining, it's considerably less. It's orders of magnitude less. And then transport to the UK. And finally, the CO2 absorption at the end of life. The kilogram CO2 per kilogram of product, we have worked this out as 0.374 kilograms carbon dioxide per kilogram of the iconic board product. And these numbers are only useful if compared to other things, really. In some ways, I mean, it's useful to know for other aspects, but in terms of calculating the carbon associated with the whole building, these are very useful elements to have. As you can see, it compares very favourably against even against plasterboards. It's competitive. These figures are taken from IC's inventory, so these are publicly available too, and we've just brought them together as a comparison. It's interesting that it compares against hardboard. It's considerably better in terms of being low carbon, and plywood, as well as having other advantages that David mentioned earlier on. So that's where I wanted to point out that the difference, if we were to use gas in the process, it would reduce it even further. And from that point of view, it becomes best in class from that point. At that point. So to conclude, the iconic board from our life cycle analysis, and the life cycle analysis can go on for a long time and become very detailed. This is a fairly short piece of work, but we conclude that this is a very low carbon product, and that although the process uses energy, and it will, by its nature, because it's made in China, have higher emissions factors because they use so much coal in their electricity and in their general processing, that the high reabsorption of carbon dioxide into the product gives it a much better life cycle analysis than other materials. This is important. It's a very key important element of this. If it didn't have that, it wouldn't be such an attractive product. So it is manufactured in China, and despite that, of the whole life cycle analysis, only 20% of that is associated with the transportation. If there were ways to reduce emissions associated with that, that could also make quite a significant difference. So it's obviously the two elements moving the raw product, magnesium oxide, from the north of China, 3,500 kilometers is a long way. But these are issues probably wherever the product was made. And it's clear that this investigation is throwing up ways that we could further improve the product by reducing it, doing things to reduce the carbon emissions produced in its life cycle. And I think it's clear that there's more research, I don't know, needed, but I think it would be useful, I think, probably in understanding the end-of-life process and also carbon reduction in the process. And that is maybe easier done here, but obviously in a place like China, trying to work these things out could be very important, but it also raises challenges from doing it at this end. So I think that this will enhance the environmental credentials of the product further. And that's it. Thank you very much.
Thank you very much, Charles and David. And it seems that the product has attracted the attention of our viewers. We have several questions. Most of them are not really related to carbon, but to other aspects of this product. So here's the first question from Terry O'Hara of Dynamic Insulation Services Ltd. How does it compare with OSB3 on cost? Could you tell us, David?
Yeah, it is more expensive than OSB3, but it is non-combustible. Mm-hmm. So for our sheathing board, we've looked at pricing it less than fire-treated OSB, which we understand is about 3 times the cost of normal OSB, and ours is about twice. So we're looking at about £7 a square metre for our sheathing board compared to OSB.
I see. There is a question from Gloria Law of OISA Designs, and she's asking, what is the sound dampening measurement in normal wall construction? Has it been tested to requirements of Section 5 of Technical Standards on Noise to recommend dB reduction and beyond?
No.
Not yet.
We have, acoustics is one aspect that we haven't tested yet. We've done our own sort of sampling and testing, but we haven't done it to the UCAS standard that we've done the rest of the tests. And again, we'll be happy to speak to anyone who wants to look at it from an acoustic point of view. We're happy to do it.
Mm-hmm. Okay, let's see more questions. The next one is from David Keith of Bracewell Sterling Consulting. Are there any health and safety issues with cutting the material, dust, etc.?
Yeah, we've looked at this and we've carried out a full material safety data sheet. ADC Controls in Glasgow prepared this for us. So there are no health issues with cutting any boards, MDF, OSB, whatever, in volume. Then you take the normal precautions about masks, inhalation, and make sure that you try and keep the dust out. But there's no health issues with the product itself.
Mm-hmm. Gary Mees Architectural Technology is asking, what is the thermal quality of this material?
The thermal conductivity is about 0.25. So again, it's comparable with other board materials.
A question again from Gloria Lowe. What is the recycling process and its related carbon greenhouse gas emissions? That's what you pointed at the end.
Yeah, it's a good question. I did cover that one. I'll go over that one rather quickly. What we've assumed, and again, we're making assumptions here linked to how other building materials are handled, but effectively, if it's likely, because of its types of use, it's going to be, it would be removed from the buildings probably by hand. So it probably manually removed, maybe some demolition, but then the transportation we've assumed within 10 kilometres to a processing site, and that would seem about right for most city centres. So that's the assumption that we've made on this. In terms of recycling, I think that the product could be easily ground up and crushed. That's something that we know, but there's obviously something that we're going to be looking into. Going into a landfill, if it was to go into a landfill, then really the amount of carbon that's in there is so inert that it really produce a minor amount of emissions, if any, we think.
On that point, we are interested in looking at what the potential is for recycling the product, what alternative uses there may be when the material is crushed down, because we know the constituent parts all have other uses. The magnesium is used in agriculture, it's used in other industries, same with magnesium chloride. We'd be interested to know that when we crush the board or try and recycle it, whether we can then use those materials for other uses. So we've spoken to Zero Waste Scotland. We're hopeful that we'll get their assistance to look at this. Again, if anyone's got any ideas of what might be a potential use, then we'd be pleased to hear about it.
Thank you. A question from George Lomakis of Glasgow, Caledonian University. What is the density of the product? Do you know physical properties?
Yeah, it's about 1,000 kilograms per cubic metre.
Then a question from Jim Hart of Edinburgh Centre for Carbon Innovation. Regarding the carbon comparison with OSB, plywood, etc., do the figures used include allowance for carbon storage?
No.
No. Okay. And a question from Bruce Newlands of Craft Architecture for Charles. Could other products be lower in embodied carbon if produced in China?
It's a good question. I think without going into detail, I suspect that it depends. We're making certain assumptions around the data. If there's energy used, because in general in China they use still a lot of coal, so their energy mix is still towards coal, heavier towards coal. That has an impact on the overall emissions factors. So if the products are made using energy, highly reliant on grid electricity, then it could even be that they're higher than, say, if they were manufactured in Europe. But there may be other elements that we don't know. So it's a little bit difficult to answer that question without really knowing what product, what's the process, what are you looking at. So it could be more and it could be less. So that maybe doesn't make it any clearer, but that would be my view.
Okay, Terry O'Hara would like more precise information on the price. Is the £7 per square meter for 9mm board?
£7 per square metre would be for the 12mm board.
12mm board.
So 9mm board would be about £5.80, £6, just short of £6 per square metre for 9. And 9mm is category 1, has got category 1 racking strength. It can be a straight replacement for OSB. So that answers it.
Okay. While we are waiting for other questions, I have also some questions. I'm especially interested in health and safety, especially indoor health. Are there any emissions from this board? Have that been tested?
There are no additives other than what we've looked at in this life cycle analysis. So there's no benzenes, no formaldehydes, The board doesn't off-gas the way that OSB is repudiated to and other plywoods. There has been some studies done in America where people who suffered from allergies actually found if they used magnesium oxide boards as an internal lining board, then their allergies were less affected. So we believe it does contribute towards a healthy indoor environment.
Also, how does it react when in contact with other materials or chemicals? Has that been tested at all? Because in construction and building, we have different materials coming together. What happens then? Are there any chemical reactions? Anything that has been tested?
There has been no chemical reactions in all the tests that we've done. There's been no indication that there's any issues. There has been issues in the past with certain qualities of material where you do, and that's one of the reasons that we've gone to a particular factory that we've gone to with the processes that they have, because they know what's going into the board and they know how to make it safe and secure. There aren't any detrimental impacts with other materials. We use it with nails, screws, we've put it on steel, wood, we've clad it, we've rendered it, we've painted it, and there's been no adverse effects at all. So.
A question from George Lomakis of Glasgow Caledonian University. How does this product deal with moisture absorption?
The product is it's hydroscopic, so moisture, it does take moisture. It doesn't suck moisture into it, but it does absorb moisture. It doesn't affect its stability, its structural integrity, and then it releases the moisture, so it dries out. So it's ideal for breathing walls, etc.
A question from Gloria Law. Is it possible to use this board as an external lining?
Yes.
Has it been used anywhere?
What we've done is we've put it through the ETAG 004 test with a render finish and a MOT 22 test with a painted finish as an external panel, and then put it through the equivalent of a 25-year freeze-thaw cycle, and it's passed both of those, so it can be used as an external board.
Again, we are waiting for more questions, but another question from me. Are there any examples in Scotland where this material has been used?
There are one or two. We have spent the last year testing and making sure that this board is fit for purpose. And that has taken a good number of months. So we have sold to timber frame manufacturers, but we're not just selling to Scottish companies. We're finding there's more interest down south. I think it's just a function of there's more, unfortunately, economic activity down south. And so it's been used more down there than in Scotland at the moment. It's been used in a couple of smaller timber frame developments.
So it's mainly used on timber frame structures?
At the moment,
that's
the simplest use, because it can be a straight replacement for OSB, using the same tools, same skill sets, etc. But we're looking at higher end applications for it because of its non-combustibility and its fire resistance. So we're looking to find those applications.
There is a comment and question from Benedicte Ranum of SE Info. Given that the board has no harmful emissions, I take it would be a good product to use in passive house construction. She's saying, sorry, that's been mentioned already, I arrived late.
We hope so. And we're conscious that PRE at Ravenscraig and the Innovation Park have got a passive house for one of their plots. And we've spoken to Gregor, the architect there, and we're hopeful that he'll see the benefits of this board and we'll be able to incorporate it into that project, hopefully. But we think it would be ideal, particularly with the life cycle analysis we've now carried out, confirming it's a low carbon product, together with all its benefits, then yeah, hopefully.
There are no other questions. So at the end, what are the plans for the future? What you would like also to test or develop any projects?
Our plans for the future are very much to continue to test the board and to seek out new applications. And we have a list of potential places with this, but we think this board will be an ideal replacement for what's currently used. So we are speaking to a number of companies, and we welcome discussions with anyone who has any ideas, have a situation or a problem that they need solved, or whether they already have a product and been combining their product with our board, we can create new products. So we're very much into looking at the new systems and trying to develop them for new ideas. Yeah.
And Charles, do you have any also suggestions on future collaboration, or how other products maybe could be assessed for life cycle carbon?
Yeah, I think that this is something that my interest is, I suppose, twofold. One is understanding and developing the systems for comparison, because obviously these boards have a very low carbon impact, if you like, and trying to understand that. I think that there's a lot being talked about, but there's maybe not a huge degree of consistency and approach. I think that that's something, with my academic head on, I think that would be more helpful how that's taken forward. We've got the University of Bath's life cycle analysis, the inventory of carbon and energy, which is excellent, but it's probably maybe more of a sort of industry-wide approach. How do we categorize these things really well? And one of the things that we noticed in doing this work is that there was nothing from any other company on life cycle analysis of these magnesium oxide boards. Now, why would that be? I don't know. It's maybe that it's not important enough where they're being used, or that actually when you get into the detail of it, it is so complicated. It is really quite complicated. I think in looking at this product, I think that there's probably other uses at the end of life use, and I think that it's important that we understand how it can be used beyond its use in construction, and so at the end of life, or I think that there's probably a lot more potential there. So some research on that, and I don't know. I think the other thing is how you could work it with other materials and actually cost it into sort of further low carbon rolling design. So those are some ideas. I'm sure we could go on and on, but that's what I would say.
Yeah, well, and then also you talked about there's nothing been done in this before. The magnesium oxide boards in the UK and in the West are relatively new. They have been used for a long time in China and the Far East, but they're relatively new. I mean, the last 10 years and more recently. If people haven't seen magnesium oxide based boards yet, I'm sure they will see some soon. Not all MGO boards are the same, and that's what we've tried to bring out in this life cycle analysis. It's very much that's our method of manufacture, our way of getting our raw materials. There's different ways of doing it. We are, as Duncryne, are keen to work with and have initiated discussions with a number of other suppliers of this type of material in the UK to try and get a consistency of approach, so that we're all dealing with a board that's fit for purpose. It might have different attributes. Some might be better fire resistant, some might be stronger, but they all do a proper job. Just to keep this, the industry, get it started off on the right foot. So we are happy to work. Duncryne are happy to work with others as a sort of collaborative approach to this.
Here is a suggestion from Gloria Law. How about a thermaline type product, insulation bonded board?
Yeah. I think the thermaline product, I think it's a plaster board with insulation on it. I think the price point for that, we wouldn't compete with directly when we add our board to the insulation, but it's something that another architect has mentioned to us. Because we've got the fire resistance and as an internal finished product, then it's definitely something that we should be looking at, because it might allow us then to upgrade the whole wall as well as being thermally insulated, it's fireproof. So yes, that's definitely something we're looking at. But Gloria's got any other suggestions or help in that regard, I'd be happy to hear them.
It occurred to me that we could ask a question. Could these boards be produced here, manufactured in Scotland?
The only reason that they could be, there's nothing in the manufacturing process that's uniquely Chinese. It's just the availability of the raw ingredients and how cost effective it is to bring the raw ingredients and how available they are and available in the right qualities to bring to here to then set up a manufacturing facility. We're hopeful that it's a new product, but we're hopeful that it will catch on in quite a big way, and then as the demand grows, then that's something that could be considered. It has been talked about, but at the moment there's nobody seriously looking at setting up a facility here.
Is it something that could be maybe organized, discussed on the UK level to increase demand and maybe think of developing manufacturing?
Yeah, on a strategic level, if somebody can set up a factory in the UK and compete cost-wise with what comes out of China, then I think there's definitely a market for it. And as I said, people have talked about it, but I don't see it happening soon. Yes. I think we have to get the product more accepted, to be used generally. I think when that starts, then I think the impetus to set up something, whether it's in the UK or Europe, somewhere closer, will grow. Yeah.
Gloria added a comment regarding her previous suggestion about the board, that it can be used externally. Then.
It can be used externally.
Yes.
We've tested it,
yes.
We've painted it, we've rendered it, and it's passed all the E-tag and the Note 22 tests, and it's gone through a 25-year cycles, pre-store cycles, so it can be used externally.
And again, Gloria is discussing and commenting, saying, let's see if I have the right. Yes, this comment. And as an advantage to Thermaline, she thinks that there are advantages in this.
We think there are too, and anyone who's got any more knowledge or experience in that area, then we're delighted to speak to them and try and advance and take forward systems developments.
Thank you very much, Charles and David. We do not have any more questions, so first of all, thank you. And I would like also to thank to our speakers, to our online viewers for asking questions. And before we close, I would just like to attract your attention to our forthcoming events. First of all, we have a webinar tomorrow. And that is a webinar related to a study entitled Retrofit Solar PV Housing, Case Studies from 3 housing associations. This was undertaken by Edinburgh Napier University in collaboration with Malcolm Homes, Port of Leith Housing Association and East Hall Park Housing Cooperative. Then on 29th of May, there will be a webinar on achieving higher heat pump COP through the use of rooftop thermal solar collectors. Again, a study undertaken by Edinburgh Napier University and European Energy Centre. And finally, on 1st of June, we are organizing a live conference entitled The Circular Economy, New Opportunities in Design and Construction. The keynote speaker will be Dame Ellen MacArthur. As this is a live conference, you will have to book places online and to attend in person. You can access our website to find more information about all the speakers at this conference. So we look forward to welcoming you at our webinars and at our conference, and we would like to thank you for watching this webinar. Thank you.